And of course, during the discussion, you will be also able to ask questions by unmuting yourself and ask out loud your question. But it would be nicer if you have questions during the presentations, just put them in the chat and we will try to make some kind of order who asks first, and so that we don't miss questions that are burnt. After the workshop, the idea is that we produce some kind of document that collects the recommendations, the discussions during the workshop. We have note takers that we have asked from our group to take notes during the whole presentations. We will send to all of you this document when it's ready, and you will be asked to contribute to it if you like to. And this document will be sent to NIST as the recommendations and the feedback from the community. If you are a speaker, please send me your slides so that we can also put them online on the website. And as I said, the workshop is recorded. I asked already the presenters yesterday, no one objected. Any questions to the rules, any suggestions at this moment, if anyone has anything to say? If not, we continue to the program for today. First, we'll start with the presentation from NIST, where they will talk about the threshold roadmap, the validation, the goals, and the pointers for the discussion of this workshop. And they will have about 15 minutes, which also includes 15 minutes of questions and answers, which should be focused mainly on the process of the standardization. Then we have two presentations from academia by Vincent Ryman and FX Standard, who will present their views and their recommendations to the document. And after a break of 5–10 minutes, we will also have two presentations from industry, also with feedback and recommendations. So now I give the word to Luis, I guess, first, who will, I'll stop sharing my screen so Luis can start sharing his. I don't hear you. Yeah, okay, now we hear you.
Can you hear me well? And can you see my screen?
Yes. Please maybe start presenting yourself first.
Sure. Actually, let me just start by thanking very much the organization of this workshop, namely Svetlana and Vincent, for organizing and for inviting us to give the opening talk. It's very fortunate for us to have this group of researchers and stakeholders getting together to talk about threshold cryptography and possibly putting together some recommendations and feedback. This is a presentation related to the threshold cryptography project at NIST. My name is Luis. I am a contractor at NIST, employed by Strativia. This is a joint presentation with Apostle Vasilev, which is who is with the security testing validation measurements group at NIST. And overall, we are part of the threshold cryptography project, which currently counts also with the participation of Michael Davidson, who is also an author of the roadmap, and collaborations by Rene Peralta, Dustin Moody, and Hassan Munawar. And possibly this is a group that will grow across time. So this is a presentation composed of two parts. I'll give the first part and then I'll pass it on to Apostle. And I'll start with an introduction on crypto standards at NIST and how the threshold approach comes about, and then I'll move on a little bit to provide the context of the threshold crypto project, and in particular some aspects of the new NIST internal report, of which a draft is out for several months now, and the final version should be out just any second, basically.
Luis, just a second. Can you make?
And then I'll pass on to. Go ahead.
Can you make the screen full, the slides full screen?
Oh yes, Thank you.
Yes, that's better.
Is this better? Okay, great. Thank you. Then I'll pass on to Apostle, who is going to talk some aspects of testing and validation, and then we'll go into some topics for a structured discussion, and then we hope to have some time for questions and answers. And basically, this aligns with the goals of the presentation, which are also shown here below. Some of the slides contain some details which I will not get into, but we basically built the slides also for further perusing for whoever wants to take a look at them after the presentation. Okay, so let's start with introduction. So basically, NIST is organized in laboratories, and it's within the information technology lab that that crypto takes place, along with other fields, generic mathematics, statistics, etc. Then within each lab, we have several divisions, and it's essentially within the computer security division that we are interested in cryptography and security. Two groups in particular, the cryptographic technology group and the security testing, validation, and measurement groups, are the ones that deal more closely with cryptography. The cryptographic technology group basically doing standards for cryptographic primitives, and the SDVM group deals in particular with validating cryptographic implementations, cryptographic modules. So there's kind of a pipeline of work here that goes together. Now, with respect to standards, NIST has a number of different publications that are of interest. We have the so-called FIPS, which is the Federal Information Processing Standards. These are usually the ones that are formally called standards, and examples of this would be AES, SHA-3. Then we have what we special publications, and in particular SP 800 stands for Special Publications in Computer Security. These are often called recommendations or guidelines, but within the scope of this presentation, and more broadly within the scope of our project, we are calling all of these things standards in a loose way. And then we also have NIST-IRs, which stand for NIST Internal or Interagency Reports, which usually have research findings or preparatory work, and those are NIST-IRs are the types of documents that we've been using to essentially initiate this project. Now, these standards are usually done, and preferably with collaboration with stakeholders, and stakeholders may come from government, industry, academia, and also other standardization bodies. So NIST standardizes cryptographic primitives, and usually it focuses on what we may call basic primitives, things like block ciphers, DRBGs, hash functions, signatures. For the purpose of this presentation, we're going to be focused on block ciphers. It's also worth mentioning that NIST itself also issues some, also has some standards that deal with other standards and with how to apply or develop other standards. Just as some examples, we have, for example, NIST-IR 7977, which describes a number of principles that should be followed when developing cryptographic standards. We have an SP 800-175 that provides some guidelines on how to choose and use cryptographic standards within the federal context. And then of maybe more special relevance, of a special relevance to this project, also FIPS 14, which describes security requirements that need to be followed when cryptographic standards are implemented for use in the federal context. Apostle will talk a little bit more about this as well in connection with the cryptographic algorithm validation program. Okay, so there are several ways of developing standards at NIST, not all of which are of the form of NIST developing standards and protocols. So that can happen. So NIST can develop standards. It can also do it with the collaboration from other agencies, but it can also adopt standards that have been developed by other standardization bodies. And in some cases, some of which are well known, such as again AES and SHA-3, they can be obtained upon a process, a long process where there's an open call for contributions and there's a competition, or what we could call a competition-like process, where in this case competition-like would be something where it's kind of a competition, but there's some flexibility to adjust the final protocols and algorithms. We currently have several ongoing projects, and some of the highlights would be the post-quantum cryptography project, the lightweight cryptography project, and the threshold cryptography project, each of them with their own scope. The focus of this presentation is on the threshold crypto project, and in particular, we will be talking about this, what we call the single device track. Again, kind of as an explicit disclaimer, in this presentation and within the scope of this project, at least at the current moment, we make a loose use of the term standards. So this may mean recommendations, guidelines, reference definitions, not necessarily the final FIPS type of document. And of course, we are projecting a vision, but no promise implied in what we're putting forward at this point. Okay, so NIST develops basic standards for basic crypto primitives. Should we stop there, or do we still have things to be concerned about? Well, we all know that security hinges on good applications of cryptography. Of special relevance are the cases of primitives that depend on keys. Usually keys are this important often a single point of failure. That's we reduce the security of a system to the security of a key. This security can mean several things, typically secretness of the key or confidentiality of the key, integrity of the key, and availability of the key when it's needed. And this is required for what we describe here as two types of things: for implementations that use these keys, and also when we have an implementation, then we typically have an operator that uses graphic implementation. And the problem is that sometimes both the implementations and or the operation can go wrong. In particular, this can happen because attacks exploit differences between what we sought to be the ideal model versus what is really the real implementations, or sometimes because we have rogue operators that simply decide to use the cryptographic implementations for bad purposes. And so one of the big questions we have is, how should we address single points of failure, typically related to cryptographic keys? And that's how the threshold approach comes about. It's an approach whereby using some sort of redundancy and diversity, we are able to mitigate the compromise of a certain number of components in a system in a way that the system continues to deliver the security properties that it should. This approach can be seen within two main paradigms. One of them is the multi-party, where each component is essentially an agent or a party that is separate in space. But we can also look at this from a single device approach, where even though it's a single device, we know how the components are established inside, and so maybe we can still have some kind of threshold approach and take some benefit from it. So at a very high level, when we have a threshold property, we often refer to this property that we can withstand up to F compromised components. F would be the compromised threshold. Often we have a dual perspective where also K and threshold schemes, where K is actually the number of participants that need to be present honestly in order for a computation to go properly. Again, one of our main properties of interest is the confidentiality of the bits of the secret key. And we know that this approach also enhances resistance against side channel attacks. As an example of referring to thresholds, consider the simple case of 3 out of 3 enciphering, let's say a block cipher. We would say that 3 nodes need to be present in order to encipher properly with respect to availability and with respect to key secrecy. We retain confidentiality of the key as long as one share of the key remains secret. Now, what this means in terms of thresholds, availability, is actually, in terms of availability, we don't tolerate any fault. So really the threshold F would be 0, and this threshold K would be 3. However, if you refer to secrecy, the threshold is 2, because even if 2 shares leak their secrets, one of them is sufficient to keep this confidentiality of the key. And this example is only basically for the purpose of showing that when we talk about thresholds, we need to characterize which properties are we talking about. And even if we do that, we know that just mentioning k out of n or f out of n is not a sufficient characterization for a comprehensive security assertion. There are other things that affect security. And so, for example, one of the things that we've done in our initial NIST-IR last year was to put forward a number of what we call characterizing features, things that should be well described before we even ask the question, is a threshold scheme better than an unthreshold scheme? These things include things like communication interfaces, whereby the nodes communicate between themselves, the executing platform, setup assumptions, maintenance aspects such as can we rejuvenate the share if it has been compromised, or just proactively across time. And we know that each of these features has several options, and a choice of different options will affect security in different ways. And so we should characterize this in order to be better prepared to make security assertions. One point that is noteworthy, namely for this, for the current context of this workshop, is also a question we can ask. Well, what if we've been talking about f out of n, but what if all nodes are in a certain sense already compromised from the beginning, in the sense, for example, where what if all of them are already leaking in some sense their secrets? Well, the threshold approach may still be effective if in practice it increases the cost of exploitation to the point where attacks become infeasible. And that's the typical case where we consider that an internal threshold design may increase the cost of certain types of exploitation, such as, for example, via differential power analysis, to a scenario where the attacker would require, let's say, an exponential number of traces. Now, some of the challenges that we incur here are basically asking or answering, okay, what if these models are actually realistic? Which of them actually are in line with the attacks that are feasible? And even if these models are realistic, what are the concrete parameters that we should choose? Okay, so this is basically how the threshold approach comes about, and that's the baseline for the threshold cryptography project to appear. So let me talk a little bit about that. So broadly speaking, the scope of the project is to look for the potential standardization of threshold schemes for cryptographic primitives. Our current milestones include our first NIST-IR, where we 8214, where we posed a number of initial questions. The intention was also to gather the community around this endeavor. Then we had the NIST threshold cryptography workshop, where essentially we got a lot of encouragement to continue this project, and got very useful insight. And now we have this new NIST-IR, which essentially puts a roadmap towards achieving criteria for considering more concretely threshold schemes for cryptographic primitives. So some of the main high-level points are that we have currently explicitly split this project into 2 tracks. One of them is a single device, so another one is about here. And some of the main points are really that we have very consciously is that we need and we want to engage with stakeholders. We really want to receive feedback. That's a priority in this project. The thing that lays ahead of us right now is that we need to define criteria for possible calls and evaluation of threshold schemes before actually thinking of any kind of standardization. And we do need to raise all the threshold schemes, the models that we wish to talk about. Okay, so we have this document, which should be published anytime soon, any second. By the way, the title has actually changed since our draft, so it's currently called NIST Roadmap Toward Criteria for Threshold Schemes for Cryptographic Primitives. Essentially, and still at a high level again, this NIST-IR presents what we could call coordinates, in a sense that it presents a structure that allows us to identify well what we want to talk about. So it has this in domains, primitives, modes. I'll talk about it in the next slide. It identifies a number of features that we consider relevant, things related to security, configurability of schemes, the aspects of validation, and also aspects of modularity in terms of the building blocks that we have and how we put them together. It describes the envisioned phases of the process, and again, it highlights the importance of collaborating with stakeholders. So in terms of the structure that we have to talk about potential schemes, we have these two domains, which essentially correspond to the two tracks of the project now, single device and multi-party. And for each of these domains, we can talk about cryptographic primitives, for which we can conceive threshold schemes. And now, even when we focus on a primitive, we can consider several ways of having threshold schemes for those primitives. Some of the points that are important here is that even though this is useful for us as a map and a way of defining particular items for possible standardization, it does not mean that every item is suitable for standardization. So in particular, one of the things we would like to have from stakeholders' feedback is to have pointers to understand what are the items for which there's really a high need in the real world and for which there's a high potential for adoption. And those would be more likely the kinds of things that would be standardized. And overall, within the standardization effort initiative, some of the things that we would like to achieve as an end result is that we improve best practices of security, namely with respect to implementation of cryptographic primitives. Possibly we set a minimum set of defaults for security and implementation. It would be nice if the things that are being looked at from the standardization point of view would improve interoperability, and it would also be good that they do not hinder innovation. That's one of the particular types of feedback that we've been having across some of our NIST-IRs. Okay, let's take a look a little bit at the single device track and why is this separate from the multi-party case? Well, typically we are considering the case of a rigid configuration of components. So think, for example, of a chip that has a circuit with a particular number of wires. Typically, we consider a circuit as a fixed layout of wires. There may be exceptions. There may be technologies that provide some exceptions, but this is in high contrast with the multi-party setting, where we can have parties coming about and disappearing and connected in strange ways. In the single device setting, we have a strictly defined physical boundary. So in particular, we consider attackers that can actually have the device in their presence and then can perform certain types of attack. And usually whatever we call nodes, be it the wires or tiles or something else, they usually communicate using a dedicated communication network. So we're not really considering the case of communication over the internet. So our current focus is on block ciphers as an initial starting point. We want to consider two main scenarios where we would build upon. And one of them, we can call them the less complex, is the case of an AES threshold circuit design where we would achieve enhanced resistance against leakage, where the attacker basically does not interfere with the communication, but can listen in to side channels. And then we have the more complex case, which is what we can call combined attacks that mix in side channel attacks and fault injections. Now, having said this, there is also some research interest to hear about possible techniques that may also be applicable to other lightweight cryptographic primitives, because as we know, NIST is also interested in a lightweight cryptography. Nonetheless, we have a strong focus on AES. As I've mentioned, modularity is an important consideration. We have this notion we call gadgets, which are what we intend is that gadgets stand for building blocks that may be applicable across a wide range of possible threshold schemes. So for example, if Shamir secret sharing is something that is going to be used across most of the threshold schemes, then it would be important that from a standardization perspective, we have a good reference definition of what secret sharing is, so that we can directly apply it whenever we're dealing with a variety of threshold schemes. The same goes, for example, if we need distributed random number generation or correlated random number generation. If we can treat that modularly and then apply it in a higher level construct, then it would be nice if we can deal with that modularly. Then there may also be some modular aspects of the actual circuit construction, such as linear parts versus nonlinear parts. Okay, one other note about the NIST-IR, our present NIST-IR, is that we consider modes in the sense of what is the perspective of the client. So let me mention that we consider a model generically where, because we're dealing with cryptographic primitives, we assume that there is a client that wants to request from a cryptographic module that some cryptographic operation be performed, such as an AES enciphering or a signature or some other kind of a cryptographic operation. Now, in the convention non-threshold approach, which is depicted here in the upper figure, we have the client. It sends a request, it receives a reply. Now we can consider, for example, a thresholdized cryptographic module that it has an internal thresholdization, and the client does not even know whether or not it's talking with a thresholdized module. In our report, we consider this, even though we focus a lot on interoperability, we consider this exceptional sophistication on the side of the client, which is, okay, maybe we want to allow the client, if that is useful, to also be able to perform secret sharing and or reconstruction of outputs. And this is just to say that we consider the cases of modules that are thresholdized and for which the actual input is already secret shared and or which only provide the output in a secret shared manner. Some of these aspects, in some cases, they are more intuitive in the multi-party setting. In any case, it may be useful to consider this for the single device setting if there are applications that would show that this would be a relevant module. There's other aspects mentioned in the NIST-IR, things like auditability, for example. Is the client able to prove that an operation has been thresholdized? And we can think of a few nuances. Okay, maybe it cannot prove, but it can be convinced that something was performed in a thresholdized manner. So I'm just mentioning this to mention that it may be useful to consider these nuances if somehow they show themselves to be useful for application scenarios. So as mentioned, we really welcome feedback towards defining criteria. I'm not going to go into these points. I'm leaving them here for future reference, but later on Apostle will mention some of this. There's one note, however, that I would like to give, which is up to this moment, namely in the first two NIST-IRs, we have been careful. I mean, it has been intentional that we have not delved into state-of-the-art related work. Also as a way of not showing preference for any particular work and because we're really positioning questions at a very high level. But at the current stage, and as we initiate this phase towards criteria, now it will become more relevant to really hear about concrete research works, hear about comparisons, what are the research works that are applicable in a setting but not in any other. So we really invite the community to provide concrete feedback and to point us towards, okay, this work is very good, this work might not be so good. So again, this is just a way of sending out the message that we are really hopeful to get this type of feedback from the community. Another aspect in the NIST-IR is that we lay out the envisioned phases. Again, phase number 1 is to devise criteria for standardization. And if that goes well, then we will be in a good place to make calls for contributions and then eventually know how to evaluate threshold schemes and possibly in the end publish standards. Again, standards are being used in a loose sense and they do not necessarily intend to imply FIPS, and we hope that each phase will be open to feedback. So this is the introduction I want to give about crypto standards at NIST and the threshold approach and the threshold cryptography project. And now I will pass on to Apostle to talk about the validation aspects and topics for a structured discussion. We will have time for discussion in the end. I don't know if maybe there's a quick clarification question or something. I couldn't take it while Apostle prepares the slides.
Okay, thank you, Luis. Good morning and good afternoon to all of you. Thank you for joining us. It is my pleasure to address this audience who is so dedicated to the effort we have embarked on related to standardizing threshold cryptography. So I'm going to talk about the validation challenge. I think Luis touched upon this issue in his presentation, but cryptography is one of these fields where really from a user perspective, the security assurances that users seek in order to protect their sensitive information do come from actual implementations of cryptographic standards. And so the theoretical definitions of cryptographic necessary but never sufficient condition for delivering these security assertions. And that has been recognized for a long time, at least within the US federal government. We have established specific programs to deal with these aspects. In particular, we have a cryptographic algorithm validation program that covers really algorithm testing and scheme testing. And CAVP by itself is a prerequisite to the cryptographic module validation program, which is also known as FIPS 140-203 now, that has been transitioning to a new version of the standard. Why is this relevant? Well, for one, the US government requires that any cryptography that's used within the government be tested, the implementation of that cryptography be tested. And so that's really where NIST validation programs come into play. It is important to note that the mandate of these two programs is strictly within the boundaries of the US federal government. It does not impose mandates or requirements for the rest of the society, industry, or society in general. However, certain industries and other countries have recognized the value of this approach and have voluntarily adopted the results from our testing. And so, in that sense, the scope of our programs is much larger than actually the US federal government. And so, as we embark on this project to define standards for threshold cryptography, we have to be we have to keep a dual perspective about our work. On one hand, it is important to be able to devise standards that are testable and validatable. Okay, so in the end of the day, the true add value for our effort would be to deliver much stronger security assurances to the users of cryptography. And again, this comes from the actual implementations of cryptographic primitives. And
Apostle?
yes?
I'm sorry to interrupt. It seems that your audio is a little bit distorted. Maybe if you could come just slightly closer to the microphone, that would be helpful.
Oh, thank you. Thank you for the feedback. Let me try to adjust the microphone settings in the system here. Is this better or? Hello? Is this better?
There's still a little bit noise in the background, but I think if you just stay closer to the microphone, it will be better, certainly.
Yeah, let me try to adjust the position of this mic, see if it makes a difference. Okay, so I was saying that not only do we have to devise standards that are testable and validatable, but we also have to figure out the specific ways in which we can test and validate the specific standardized threshold scheme. So that's a challenge for all of us. So a little bit of a note on the cryptographic algorithm validation program. It is a program that is going through a change at the moment. I've been talking about the need to automate our validation programs because of the large scale or the large volume of validations we're processing each and every year. And so, so right now, we are in the process of transitioning the cryptographic algorithm validation program from the old legacy model of using a lot of human actors in performing algorithm validations to a fully automated system whose architecture is kind of briefly described here. The point is that we have developed server infrastructure and protocols, corresponding protocols that allow sort of people to submit, to request test vectors from the NIST server to perform algorithm validations. They run these data through their implementations. They submit the results to us. Our system checks them and issues certificates automatically. Related to that, we're also changing the definition of what the validation program means in terms of introducing the so-called first-party testing. Traditionally, most of the government security programs have been instrumented with this intermediary third-party validation labs that perform the testing and submit the results to the government bodies to adjudicate. We're changing that because of the fast pace of development in the industry and the need to perform very quickly validations of new products and to facilitate their adoption within the federal government. We're introducing the concept of first-party testing, where we allow the industry to establish laboratories for themselves and integrate the cryptographic testing deep into their product development life cycle, such that they can really do continuous testing of their product lines as they continue to evolve and be able to obtain validation results much quicker than in the past. So, so that's a significant change. And as we embark on our effort for developing threshold cryptography, we should be mindful of the kinds of mechanisms we are putting in place to automate the testing and minimize the human involvement to the extent possible. So looking forward, how we see this effort evolve, I would like to pose a certain set of topics for our workshop to consider and provide necessary feedback to us in order to be able to successfully drive the threshold standardization effort forward. In particular, we need to sort of narrow down the types of attack that we want to consider as most important for the single device track of threshold crypto. Whether they'll be active versus passive static versus adaptive, stealth versus detected, etc. We have to also recognize that often we cannot just focus on one single property and forget about everything else, because often it turns out that improving a threshold security threshold scheme against a particular attack may actually result in a degradation of another property in another setting or another application. So we have to look at it from usually several points of view. And Luis already touched upon this, but of particular interest to our group is two starting points. We would like to consider passive attacks where AES threshold circuits protect against leakage, and another active model where AES threshold circuits protect against combined attacks, which include leakage and fault injection. So again, just reiterating the same thing, resistance against side channel attack is one of the main motivating points for us to embark on this effort. For many years, the hardware industry has been burdened with this problem. How do they protect their cryptographic implementation in hardware against side-channel attacks? And that was our motivating example for us to embark on the project of standardizing threshold crypto as a major or the potential mitigating, very effective mitigating factor against side-channel leakage. And then, of course, the resistance against combined attacks, where we consider the possibility of leakage and fault injection. The question here to the community is, in particular, how do these two models relate to each other? Can we say that one is superior to the other and think of it as a high level of assurance overall, or are they just different models? And that's kind of a question that we'd like to get some feedback on in order to be able to position the various schemes that protect against side channel only or the combined attacks, either as equivalent modes or maybe think about providing different levels of assurance within the cryptographic algorithm validation program to indicate that some implementations are more secure than others, whatever that may mean. Different other questions, some other questions for the community to consider. We need to be able to enumerate and define the desirable property that that the particular threshold design can achieve. We need to be able to identify the useful construction paradigms that can be used not just in that particular scheme, but across many. We need to be able to describe, identify the modes or the conditions under which the threshold schemes may enable the resistance against specific side channel attacks or combination with fault attacks. And we need to identify the possible parameters, all necessary interesting parameters, such as, for example, the masking order and the number of shares, that would allow us to realistically characterize threshold designs, so that we can understand what are the security assumptions associated with each and every one of them, how many of them are actually testable, and what are the parameters associated with this testing to know how much to push it to gain the necessary assurance that we've done it properly, and we can assure the public that if they use a particular product or a module, they get what they want. And so other relevant aspects of feedback we're thinking are the motivation or the applicability. What are the potential application domains that can be addressed with specific standards? What are the concrete protocols and algorithms? In particular, a good overview of the state of the art. Luis noted in his presentation earlier that we have refrained ourselves to make this judgment ourselves, but we would rely on the community to give us an objective view of what is considered the state of the art and what are the best algorithms or protocols to consider for standardization. We're interested in gaining some understanding and maybe accumulating even reference implementation in order to be able to assess feasibility, to benchmark some of the results, and of course we favor open source, and it would be nice if we can accumulate at least the submissions that are going to come our way for standardization, to get them in open source form so that we can have an open and transparent discussion about their properties. And another underlying issue related to proposals for standardization is obviously intellectual property. What are the known patents, licenses, things that could interfere with the openness and the ease of adoption of standards. I'm not saying that these are necessarily showstoppers, but it's good to know what we're getting into to be able to give the right advice and suggestions for people interested in using these standards. There are other considerations that we seek your input on, in particular, the modularity challenge. When we're talking about threshold cryptography, the complexity is high. There's many different approaches to look at it. And so the question is, how can we figure out what are the right building blocks that can be used not just in one particular scheme, but in a number of different complex compositions? And so that's really a major question that we're asking you to give us input on. What do you think are the primitives within threshold cryptography that would be useful to identify on their own and be used in a number of different contexts? And with that, let me finish with some concluding remarks here. First of all, I noted several times, and Louis did himself, that we rely on you as our stakeholders to give us good feedback so that we can devise the right criteria that will serve the needs of the community at large to really standardize the best standards in threshold cryptography, best in terms of security, best in terms of ability to validate, to test and validate, that will actually deliver the security assurances that our users are seeking. We have a very large theoretical space of threshold cryptography, and so we need to figure out a rational way to move within it and select the right threshold schemes to focus on. And related to that, obviously, we count on you to help us understand what are the best, the most robust threshold schemes and models to focus on. I noted that automated validation is an important part of our development, standards development process. We don't want to just come up with threshold schemes that have wonderful theoretical properties, but we would like to be able to verify in a very real way the validity of all the security assumptions that go in supporting the security assumptions each of these schemes portrays. And so on top of that, I indicated that because of the large volume of validations we do every year, we really have to think about an automated computer-based mechanism for validating these assertions. And of course, again, our way of interacting with you, our way of deriving the standardization process consistent with the way NIST has always done it, is to be open, to be transparent, to rely strictly on the technical merits of proposals, to establish trust with you and with all the stakeholders in our community, and to be able to drive the standard process successfully to an end. And with that, I'm going to just give you a few pointers to relevant documentation about this project and our contact information. Thank you, and looking forward to working with you to a successful end.
Okay, thank you, Apostle. Yeah, we apologize for the bad audio quality, but yeah, this is what it is. We hope the rest of the participants the presenters will have a better quality of audio. But if you have any questions, we only have about 5 minutes for questions left, but still, if you have any questions, please unmute you and ask. I don't see any questions in the chat, but you can still ask live questions.
I have a question. Do you have a kind of timeline for the process?
Well, we're starting today essentially with a single device track, and we would like to move as quickly as the community is ready to work with us. I indicated that we rely heavily on your input and involvement throughout the process. So it will be dependent heavily on the ability of the community to organize, provide us with effective input so that we can move quickly. Our intent is to move as quickly as possible, but it will depend on you as well.
Yeah, and I would complement with what Apostle is saying. So move quickly as possible, slow enough for proper scrutiny by the community, and we have identified that we should be flexible to have different timelines for different possible items for standardization, including across tracks. So I guess the short answer is that we don't have a concrete timeline yet, but as Apostle said, hopefully we'll move swiftly.
One other point to add is that in moving in this standardization effort, we're willing to start with the relatively simpler approaches in order to establish some experience with them, and then evolve to more complicated constructions. And so if
We lost you, Apostle. Yeah, maybe. Yeah, I have a small question as well.
I think we've given the gist of the answer nonetheless.
I have a small question as well. The change of the name of the document that you mentioned, moving now to a roadmap toward criteria, does it mean the final result will not be a standard, or it's just not clear yet what exactly will be the final?
So first off, this is based on internal feedback that we've had. This is for us a way to emphasize more clearly that what is standing right before us right now is devising criteria. Standardization, we want to make clear that it can have several meanings in the end. There's several possible end formats. And so we found that it would be more clear to focus on the aspect of criteria, which is clear what it means. And the actual end results of standardization, they will become more clear as we move along.
I'd like to add a couple of things related to that. Certainly, the end result.
I think you are muted.
Am I muted? Can you hear me?
No, you're not, but it just breaks once in a while.
It was just a delay.
Can you repeat?
What I was going to say is that the end result of our effort is definitely going to be a standard, but standards a number of things within NIST, and most people associate the standard with the FIPS, and we don't want to necessarily make this determination up front. As you know, some of the most actionable block ciphers are actually special pubs. The modes of AES, for example, are defined as special pubs, and yet they're quite widely used and well-established standards. So we'll find the right mechanism to position these things as standards, and not necessarily, but we don't necessarily commit to a FIPS document. That's what we're saying.
Okay. Any other questions? We have time for one more question if there is any. If not, thanks a lot to Luis and Apostle. Please send me your slides so that we can put them available on the website. And we move on to the next points in the agenda, which is two presentations from academic point of view. And Vincent is the first speaker to start.
Okay, I think now I'm unmuted.
Yes, you are.
Okay. Good afternoon, everybody. So I will talk about threshold cryptography against physical attacks. Maybe one of the most important insights that we got in the last 20 years, at least in the public research domain, is that the so-called black box setting, where an attacker can only look at plain text and ciphertext and has to find out the key, that this is kind of textbook model, and that in many applications we are more confronted with a gray box model, where devices also leak information about their computations, where devices can be faulted, and where we need to consider implementation techniques as well as mathematics in order to assess the security. And popular countermeasures against side channel attacks, I think there are two large categories. One is hiding of information by reducing signal, basically by reducing the signal to noise ratio, and by making sure there is less signal and there is more noise on the device. That will not be the topic of the presentation. Another one is what the hardware designers have for a long time called masking, but what we can also call secret sharing. So where instead of just implementing an operation that works on plain text and produces ciphertext, instead we will share the plain text in different shares, and also the ciphertext will be shared, and we have to think of another kind of function that transforms the input shares into the output shares. Countermeasure against fault attacks, on the other hand, consists of adding redundancy. So in some sense, this is the opposite of what we do if we want to add resistance against the side channel attacks, because in the top figure, we usually assume an attacker needs to recover all shares of a variable in order to get the variable and to get information. Whereas in the lower picture, there are also several fields, but they are redundant. So there, an attacker who has access to one or a few of them can recover already the secret. So these countermeasures, in some sense, counteract each other. If you have secret sharing, it becomes more easy for an attacker to introduce errors. If you add redundancy against errors, there is a risk for more leakency. Techniques that are also used in the countermeasures against fault attacks is detection, correction, or effective computation, where we try to ensure that the output of the circuit is garbled if a fault is detected. And so a topic of ongoing research is how to secure against combined attacks, how to think of efficient schemes that can resist both side channel leakage attacks and fault attacks. And so here we could say the basic idea of threshold cryptography or masking, as I showed also on the picture, is instead of working on a secret variable X, we actually split it in two or more shares, at least two. Where if you think of two shares, you can think of one as the encryption of the secret variable and the other one as the key. And then you compute outputs and combine them again. And there, the whole idea is that even if you recover the full information on X1 or the full information on X2, you still don't know what X was or I. Yeah? So this threshold crypto and masking model, as it has been developed by several teams of hardware designers, has also been described by Ishai, Sai, and Warner in their wire probe model and security there. And let's say to the more theoretical cryptographers, this is all reminiscent of what's called multi-party computation. So, because both in this threshold cryptography and in multi-party computation, data is split in shares, certain computations are done on these shares and results are exchanged in order to get the output. Yeah? And where in multi-party computation, we talk about so-called semi-honest adversaries or honest but curious adversaries. In the physical world, in the hardware world, we can see that this corresponds to side channel attacks, just eavesdropping. And what we in the hardware world called fault injection attacks corresponds then to what in the multi-party computation world is called active adversaries. So there are strong relations between the two fields. The most important difference is that costs can be different. Yeah? Costs in hardware are different from costs in multi-party computation. So protocols for multi-party computation that are optimal in multi-party computation sense are not necessarily optimal when they're translated to the physical world. And this is something that we have to keep in mind when we think about the analogy. Yeah, here we see another view, a recently introduced way to talk about or to more closely link multi-party computation to side channel resistance research is to talk about different tiles on a chip, where we think of a circuit as split up in different parts, where every part then represents a party in the multi-party computation. And then we can study schemes where a number of these tiles are probed either by means of lasers that introduce errors or by means of detection probes that collect leakage signal. Yeah? And if you then compare different countermeasure strategies, we have to look at several things. And one is, of course, the security that they offer. Do they offer security against side channels only, against fault injection only, or against combined attacks? And what is the number of probes that they allow an adversary to have, or the number of faults that they allow an adversary to introduce into the circuit? A second category of that we need to consider in our evaluation criteria is the assurance that we have. How rigorous a security proof can we obtain for such constructions? What are the assumptions used in the security proof? How the threat models? How realistic are they? And how verifiable are they? And then finally also the cost. And when we talk about the cost, we can speak about different things. Circuit area, although in many applications area is not a limiting constraint. There's also energy consumption or power consumption sometimes. Speed is important. The number of clock cycles taken or the maximum frequency that the circuit can be run at. And also the number of random bits that are consumed during the computation, which in many academic solutions currently is still quite large. We also see research proposals where speed and circuit area are highly optimized, but at the price of large consumption of pseudo-random bits. So maybe it's better here in order to reduce the dimension of the optimization problem to to go to let's say to the convention that a circuit that consumes pseudo-random bits should actually, let's say that the solution should also include circuitry to generate these pseudo-random bits and include the area of this pseudo-random noise generator into the area of the circuit, and also include the energy cost into the energy budget of the solution. In this way, we could reduce the number of items that have to be considered in the cost. And so one of these proposed threshold cryptography mechanisms, the one that actually gave its name to the current initiative, is the so-called TI, or threshold implementation technique. It was the first countermeasure proposed that was secure in circuits with physical defects like glitches. So the typical hardware effects like glitches or delayed signals are a big difference with software, and let's say ensure or cause the effect that countermeasures that are secure in software are not necessarily secure in hardware. And it took some time before we realized this in the research world. But the TI technique is the first one that took this into account, dating back from 2006. It has, it's efficient, relatively efficient compared to other similar schemes in area, in speed, latency, power, energy consumption, and it can work in any hardware technology. On the next slide, I have a few other advantages and limitations listed. So I think the most important advantage of the threshold implementation technique is that it's based on a few simple principles, that the cost is reasonable, that we can prove security in practical security models, and that it's also, well, we already have automatic verification tools. For example, the in-house developed VER-MFI tool, and that is actually a combination of two tools, one for fault injection attacks and one for masked, for side channel leakage attacks. Some important limitations that maybe should also be mentioned is maybe first the second one, and that at the moment there is no composability for TI, so we have to consider the whole circuit. Let's say we have to consider large parts of circuits. We can split up to a certain extent, but not in very small parts. And we also have to make the assumption that it is actually possible to implement this like tiles thing, where each tile can compute on one share, or can compute on, and such that shares can be isolated, and that there is no physical interaction, which translates most clearly into the fact that we cannot tolerate measurable crosstalk between different tiles. In case there is crosstalk, then the security proofs need to be changed. They don't work in their current form. So after the initial development of TI, there have been a few follow-up works, which I just want to mention here. And there is the so-called consolidated masking scheme, which trades off speed for area and random bits. There has been a research line where the private circuits 2 paper that work has been redone by using TI techniques, making it more efficient. There has been a kappa model considering security against combined attacks, and then the optimized M&M also considering security against combined attacks by extending TI techniques. So this was about TI threshold implementation. I also want to use the last minutes of my talk to give some recommendations to NIST as input for their standard. So on the threat models, I think it would be good to define a set of ranges for the number of traces. For example, we think that realistic is to consider adversaries. So for passive adversaries that can collect 100,000, a million, 10 million, or 100 million traces, we think that this, 100,000 is feasible in a simple lab. 100 million requires quite stable instruments. For active adversaries, also separation should be made, and we propose to make a distinction between attackers that can introduce 1 to 4 faults at controlled locations, meaning at controlled locations and also with a controlled effect. And then again, make a difference between how many traces they can subsequently collect. In order to make comparisons fair, it's important then to specify clearly what's the size of the fault, how one counts the number of faults, because many implementations are round-based. So is a fault stable over all the rounds, or does it just happen during one round? And in each of these cases, we should distinguish between real attacks that lead to recovery of some key bits on the one hand, and on the other hand, simple detections of leakage, like, for example, is done with TVLA method. We think that the effort should focus on AES or components of AES, and the typical subcomponents of AES in hardware implementations are end circuits, then finite field multipliers, which then lead to the AES S-box, and finally the AES round. So this should be the focus. Of course, you never know what the future brings, so it's probably good to not exclude other gadgets that can be useful for other ciphers. Finally, we think it would be very, let's say, relevant or very helpful if there would be a kind of infrastructure or specification of how benchmarking will be done. For example, by defining a few models in FPGAs or ASICs, some technology in ASIC, or else, so either a few specific choices here, or else develop a kind of easy benchmarking framework like Athena or Supercop that exists, where many different platforms can be tested in a kind of automated way, and such that implementations can be tested on many different platforms in a kind of automated way. And next to the platforms, there should also be a small number of functionalities being defined that need to be benchmarked. So one could say the full AES, or one could limit this to certain gadgets like a 2-input AND gate, or a finite field multiplier for a certain field size. Okay, this is what I wanted to say. Thank you.
Thank you. Any questions for Vincent?
May I pose a question?
Yes.
Thank you, Vincent, for the presentation. You mentioned the aspect of non-composability of TI. could you comment on what, if any, if this brings any practical consideration in terms of actually, let's say, composing an AES circuit out of AES S boxes that have been thresholdized? Does in practice this non-composability make it infeasible to prove secure an implementation of a full AES circuit? Or are there in practice ways of getting around this non-composability?
Yeah, one can get around this. Let's say the main problem is that it makes it, so if you have composability, you can split up an AES box in still smaller parts, and then again still smaller parts, and then prove security for very small parts, and then you have a proof that also the whole circuit will be secure. Whereas for AES, you have to take care how you construct the proofs. So if you have, let's say, a secure AES S-box, then it's not so difficult to from that prove security of the whole AES. But if you want to go smaller than an AES S-box, then you have to watch carefully and so forth. How the security of the subcomponents of the S-box, how secure subcomponents, how they lead to a secure S-box. Then it becomes a bit more effort to prove this. But it can be done. Huh?
Okay, thank you.
Any other question? Or we can also have the questions at the end of this session after the second talk.
Svetla, may I ask a question?
Sure.
Listen, thank you for the presentation, and in particular about the recommendations that you made. I have a question related to the benchmarking slide, the reference platforms in particular. I know that in the past, one of the assumptions around the TI model was at least to be able to show that the tiles on the chip are separated sufficiently, at least some minimal distance from each other to be effective at protecting against leakage and so on. Not leakage, but ability to reconstruct the key with the assumption that each tile leads. And I know that in the past, some of the design tools people use to develop the definitions of the implementations on specific platforms, FPGAs and things like this, were interfering with the necessity to maintain a specific minimum distance separation between the tiles. Have this been sort of resolved or improved at some level, or what do you see?
Okay, Apostle, I'll briefly repeat what I think was your question because your sound was fading in and out. So I think you mentioned that we did previous research showing that if you put data lines of different shares close to one another on FPGAs, you can cause crosstalk. And then we started to investigate if it's possible to modify typical commercial tools to make sure that they keep circuits of different tiles separated. So if this was your question, then the answer is that this is still ongoing. This has not been resolved. Let's say there are some ad hoc rules now about splitting a design in modules. So where different shares come in different modules and where you tell the tool to keep the modules separated. But we have had let's say, no contacts with tool developers where they could let's say, guarantee that this will always stay like the designer wants it. So this is still ongoing.
Thank you, Vincent. That was the gist of my question. I guess since we are a community here, we may have to ask other members of the community, in particular those from the industry, to help us convince the tool developers to take into consideration such capabilities going forward.
Yes, I think that would be very helpful.
Okay, any more questions? I propose to leave the questions for the end of the session and to give the word now to François-Xavier Standard for the second presentation from the academic point of view.
Do you hear me?
Yes, we do.
Okay.
You can share your slides and you can present yourself if you want a bit more.
Is this okay? Yeah.
Yes, we see the slides. Perfect.
Okay, excellent. So you said I should present myself? I didn't hear you.
If you like, you can. I mean, I'm not doing long presentations, so if you
Okay.
want to present yourself.
Yeah, so my name is François-Xavier Standard. I'm professor at UC Louvain in Belgium, so close to Vincent's place, and yeah, mostly doing research on physical embedded security. And in this talk, what I would like to do is to discuss a little bit, specifically the masking countermeasure that I guess we discuss these 3 days. And I would like to discuss more specifically what are the models and the tools that we can use to reason about masking. The starting point, I will give a brief background. Vincent already gave one. I will give a slightly more theoretical one. So the idea of masking, of course, is that we want to prevent this side channel adversary, and this side channel adversary is able to learn something about the internals of an implementation. You can really see this as probes. Sometimes the adversary in the probing model sees exactly the value. Sometimes it sees a noisy version of it. And the intuition that masking has is that if you split the sensitive variables, so all the internals, for example, of your AES computations in several shares, like here in 3 shares, and this is an encoding, the adversary willing to break this implementation will have at least to combine the leakage of 3 shares. I keep it intuitive now, but the hope is, of course, that combining things will make everything more difficult. And then, of course, okay, it's fine to have encodings, but we need to find a way to compute. And most of the challenge when we do masked implementations is being able to implement a full cipher, in particular, the nonlinear operations. And here I just plotted something that is known as the ISW multiplication, which is really just multiplying 2 3-share secrets together. And as you see, we need some randomness, and we assume that the adversary gets really everything. The cool thing about masking, and I guess why it's a good candidate for maybe standardization or at least formalizing, is that we have some strong security guarantees, at least theoretically. And the guarantee is that if you assume that the leakage variables, so this LAI, sorry, so this is the leakage that the adversary sees about the secret, can be written as a function of the share plus some noise. And that really means the leakage function is such that you leak about 1 share at a time, or you leak at most about a linear combination of the shares if you want to generalize, but you don't leak nonlinear functions of the shares. So that's the first condition. I will sometimes say the independence condition. And if you also have the fact that the noise variance is large enough, and in the rest of the talk, I will use the mutual information between the share and the leakage as my metric for the noise. Then we know that for a masking scheme with these shares, the number of traces to reach a given success rate is going to be proportional to a constant divided by the mutual information per share raised to a certain power. And that really means if you're able to guarantee that your hardware implementation is such that it's noisy enough and the mutual information per share is lower than 1, then you can amplify this noise kind of exponentially. And again, so very simply put, the idea of masking is to amplify the noise. I will reflect it with this mutual information by raising this noise to what we call the statistical security order. which is this value D. And this value D measures the level of independence between the leakage of the different shares. What's the intuition behind that? Why do we have something exponential? It's easy to see with, it's a 2-share example and a single bit secret. So if you take the 2 upper plots, the upper left one is the leakage distribution of a value 0, and it's shared in 2 values. So the 0 can be encoded as 0, 0. That's the lower, like this point. I don't, you see my mouse here. So it's this one, and it can be also encoded as a 1, 1. And if you have the encoding of a secret 1, which is the right distribution, then it can be 0, 1 or 1, 0. Clearly, the two distributions are different, but the important point is that if you look at the leakage vector of these 2 distributions, the leakage vectors are exactly the same. And that means that if the adversary wants to extract information from this distribution, at least he has to estimate a variance, which is, if you have enough noise, something more difficult than estimating a mean, which would be what we do when we attack an unprotected implementation. And intuitively, the idea of masking is that if you increase the number of shares, what you hope is that the adversary will be able concretely to estimate statistical moments of increasing orders. So that's statistically, and when you look at the information theoretic intuition, or what you have in terms of security in the end, we can have this type of plots where the x-axis is the noise variance, the y-axis is the amount of data that you need to collect to reach a success rate of 90% here. Everything is in log scale. And what we see is that if you're on the left of the plot where there's no noise, of course, masking is useless, because if you have no noise, you have nothing to amplify, and that's not very helpful. But when you're in the right part of the curves, you see that the slope is increasing with the statistical security order. And that, since we are in log scale, that really means that you increase the security exponentially. And that's, at least theoretically, it's a good news, because it shows that masking can give us an exponential security increase. And in terms of performance, Vincent briefly mentioned that, but like even if it was full MPC, the overheads are kind of quadratic in the security order. So we have some distance between what the adversary can do and the cost of the implementation. Okay, so that was the background. What I mostly wanted to do here is to discuss all the things that can go wrong, because yeah, if you just hear the beginning of the talk, it looks like a wonderful solution. Why is it that it's so difficult to implement masking correctly? The main reason is that these 2 assumptions that we need, so the assumption that we have certain independence between the shares leakage and the assumption that we have sufficient noise, are frequently contradicted in practice. So I will start with this idea of security order reductions. And the first thing that can happen is purely mathematical. So one issue is simply that you have a lack of randomness, for example, in your multiplication. Here I give the example of the ISW multiplication without any refreshing. And it's again in 3 shares. And if the adversary in this case is able to probe C1, he gets A1 times B1 plus B2 plus B3, which is B. And that means each time he sees C1 equals to 1, he has information on the value B with a single probe, which is of course contradicting the security order requirement. So we hope that with this scheme, the adversary will need 3 probes to collect information. So that's one thing. The other thing, even if you do refresh properly, so if you do some randomness, use some randomness in the multiplication gadgets, you can have composition bugs. So here I just show a very simple one, but if you take exactly the ISW multiplication, you multiply A by A, then you will have the situation that again, if you plot A2, A1, and A3 in 2 probes rather than 3, you can have information about the A value that you want to protect. And of course, this is very simple. The main case that we see, for example, in the ASS box is when we multiply a value with a square of itself, like in the multiplication chain of the ASS box. This is something that we see frequently, And these composition bugs, typically, they will also pop up when you look at bit-slice representation of S boxes. So at least it's something to consider. Okay, so that was purely mathematical. The next type of problems is what I would denote as physical security order reductions. Here the problem is that when you move your implementation in a device, maybe the hardware is not behaving exactly as you want. One well-known example is what we call transitions. It's pretty simple to explain. If you assume that you have a two-share encoding, A is A1 plus A2, you assume a register that contains A1, it's overwritten by A2. You assume that the leakage is then proportional to the distance between the two values, for example, the Hamming distance. And in this case, of course, this transition-based leakage is completely canceling the countermeasure because in the end, you get the Hamming weight of the unprotected A. That's one thing that can happen. Another thing that was mentioned in Vincent's talk is the problem of glitches. Here, it's a bit different. The idea is that you have some hardware function, F, that manipulates three shares, A1, A2, and A3. And it's very difficult to build the hardware in a way that you guarantee that all the transient computations that are going to occur before you get the final result of F, are not combining the leakages in a way that you don't want. And the way that you don't want to combine the leakage is typically the nonlinear way. So for example, here it could happen that this leakage Li, so this point in time, is a function of A1 times A2 times A3, which is again breaking the security order, so reducing the expected security. Good, so one thing that's important is that all these reductions of the order, so it can be because of lack of randomness, because of composition, because of transitions, because of glitches, because of couplings that I didn't explain, but Vincent mentioned. All these things can create what I call low order leakage. So you find information in a statistical moment that is lower than the one that you would expect. And how do you see that? Here it's the example with two distribution. The blue distribution is the perfect one, and the green line, I hope you can see it, is a little default that make it such that you have a small difference in the means between these two distributions. The important intuition is that if this difference in the mean values is very tiny, maybe the best adversarial strategy is still to estimate the variance, so to do the second order attack. Maybe if this difference is significant, or maybe if the noise is very large, then it's different and it becomes a problem. So you have really this idea that the amplitude of a reduction of the order can be critical or not. And what matters in the end is what I would denote as the effective security order, which is the statistical order of the most efficient attack, if you want to analyze this quantitatively. Okay. And then another type of issue is a lack of noise in the implementation, because we've seen, like here, if you're on the left of the plot, then you have no interest to do masking, and many issues can happen here. The first one is multivariate attacks. When you have the leakage of one share, usually if it's measured by an oscilloscope, you can increase the sampling rate. You have a sampling rate, you have a lot of samples, and you can combine all this information. You have what we call horizontal attacks. So that's a bit more specific to the multiplication gadgets. For example, if you take the ISW multiplication, you have this situation that the share A1, and every share, in fact, is going to be manipulated 3 times, which means that if the adversary knows that, he can average the noise of these shares and divide it by 3, or in general by D, which is very detrimental. So it typically implies that if you want to implement the ISW multiplication securely, you need to increase the noise level in function of the number of shares that you use. And finally, you have what I would denote as multi-target attacks, and this is more related to the circuit structure. Here I took the example of the AES box in GF2 to the 8. So you have many computations that depend on the same 8-bit secret. So an adversary can definitely try to combine all this information, and so there's clearly here an algorithmic dependency ciphers with complex S boxes are probably more difficult to protect than ciphers with simple S boxes. So these are all the problems we face. The question then is how to analyze these implementations. If you look again at the academic literature, I would say there are three main types of abstractions that we can use. The lower one is what is defined as the noisy leakage security, and that's the one I explained already at the beginning. That's what we want in the end, right? We want that the number of traces that the adversary collects is inversely proportional to something that grows exponentially in D. The problem is that many things are very hard to analyze if you go directly to the noisy leakage model. Typically, like all these probing problems, composition issues, and so on, I think it's extremely challenging to analyze that by just exhausting distribution. So it's in general useful to reason with higher abstractions. One intermediate abstraction is what I would denote as bounded moment security, and it's really related to this idea of statistical security order. So here the goal in the bounded moment security model is that you want to force that all the statistical moments of the leakage distributions are independent of X up to a certain value. And an even more abstract model is the probing security model, where you give the adversary the power to directly read the wires. And of course, then he has to exclude one wire from the view so that it doesn't get the secret in full. So these are very, very different abstractions useful for different things. The good news is that there are theoretical results, and in particular, there's one important result by Luc Jembowski and Faust in 2014 that shows that these abstractions are connected. And in particular, if you have probing security and you add the independence and noise conditions that I was mentioning at the beginning, this implies noisy leakage security. Or in other words, it really means that you can use the higher abstractions like the probing model to reason about or to reject certain problems. And you go as far as you can with these very abstract models. And at some point, of course, some things cannot be captured by probing security, typically anything related to the noise. And you go down and you try to use the different models in order to argue about security or to analyze the security of an implementation. I tried to make this table, which is completely tentative, but I guess this is something in the end this audience would be interested in. My view is that there seems to be a right abstraction to reason about all the aforementioned defaults. If you think about mathematical security order reductions, I would say most of the time at the moment we reason qualitatively in the threshold probing models, and then the tools and metrics that seem well suited to that are either you do handmade proofs or you use formal verification and you try either to prove the thing directly, which is probably best for efficiency of the circuit, but very expensive for the cost of the verification, or by relying a little bit on composition, which makes the verification much simpler and has some overheads in terms of circuit size. So this is a trade-off. I don't know much that is done quantitatively about mathematical security order reductions, but that could. If you think about physical security order reductions, the good news is that qualitatively, there are many things that can be done in the high-level robust probing model, which is related to non-completeness, the properties of threshold implementations, and so on. And here again, because it's an abstract model, you can use proofs, you can use formal verification, and you can decide whether you want composability or not, or if you need to leverage that. If you want to reason, I would say, quantitatively about physical security order reductions, then of course you need to move to the bounded moment model. And that's a totally different set of tools and metrics, right? You're going to use things related to what we usually call leakage detection, so t-test, higher order signal to noise ratios, statistical procedures essentially to test what is the values of different statistical moments. And finally, noise reductions, I guess you could reason a little bit qualitatively, right? If you look at a circuit or at a gadget, you can count the number of manipulations of every share, but ultimately, I think for this part, we want to be quantitative. Here you need to work in the noisy leakage model, and your goal as an evaluator is the same as an adversary. You really try to perform worst case attacks, and based on that, either you estimate the mutual information per share and you leverage the reductions because you know the statistical security order and you trust the proofs, or you directly compute the mutual information for the full implementation, which again may work for small security orders or small security levels, but rapidly is quite difficult to do. Briefly, before to conclude, I wanted to give some ideas of what we probably need if you think about what exemplary implementations give you, roughly, and I'm speaking about open implementations. If you look at the mutual information per share that you can hope, let's start from the right. The worst thing is, let's say, a Cortex M0 or something smaller, then I would say, yeah, there's no hope to implement things very securely there because the mutual information per share is probably larger than 1 anyway. If you take Cortex M3 or larger devices, then from at least our experience, the SNR can be, or the mutual information can be between 10 to the -1 and 10 to the 0. So there is a little bit of noise to amplify. If you go to unprotected hardware with a decent level of parallelism, you move between 10 to the -2 and 10 to the -1. And if you give yourself the possibility to add noise, to maybe do signal reductions, like adding some countermeasure, it's even better. And then you can take exactly the security levels that close to the security levels that Vincent was mentioning. You can say, I want security with 1,000 traces, 1 million traces, 1 billion traces. I can be in the case of a hardware implementation with countermeasures and non-protected hardware or a Cortex M3, and you can directly estimate or predict the number of shares that you will need to reach this security target, which is going to be terrible if you have limited amount of noise, right? Cortex M3, you really need to have 1 million traces, more than 15 shares, and much less shares if you have hardware implementations and a decent level of noise. Good, and what I wanted to conclude is mostly that if you think about masking, if you look at the academic literature, you will see that there's very different challenges that are raised. And I didn't even mention the challenge of performance, right? I really focused on security here. And at least in the current state of the art, it seems unlikely that everything is going to be solved and analyzed with a single model. So we probably need to think about how to use the different models to reach the properties that we want. One thing that's very important to see is that the severity of these different challenges is extremely case specific. Typically glitches that I mentioned, they are definitely more critical in hardware implementations. If you think about transitions and noise, it's probably much more critical in software implementations. And you have more things like that, right? Composition, I think it's critical if you increase the number of shares, not really, or much less if you reduce the number of shares and so on. And probably the good news is, I would say, for basic cases, and typically what I mean by basic case is an SPN like the AES, no randomness reuse, really plain masking, and yeah, not optimizing performance too aggressively. We have quite well understood published solutions, which means essentially for those, we at least need to agree on a relevant target because there can be many, but if you fix a target, I assume we can find several solutions in the literature. And I just wanted to mention as a side note that, of course, the cost is very important. If you have long messages, it's always possible to amortize the cost of the masking countermeasure because of by using leakage resilient modes of operation, and there are many options there too. And that's it. Thank you.
Thank you. We have some time, not too much, for a few questions.
May I pose a question?
Yes.
Thank you, Francois, for the presentation. it's I think it's very useful to see that certain problems need to be looked at from various perspectives and various models. The question I have is the following. So it is clear from your presentation that we need to have various models to look at the problem of leakage in a comprehensive manner. Having said that, would you say that a threshold approach is nonetheless likely to have a positive effect under all of these models, even if at varying levels? Or do you envision that there are certain models where a threshold approach can actually be degrading security?
I would say purely for side channels, right? I don't think it can degrade. I would say like the threshold approach, the good thing is you can deal with it in these very high level models. Like you play with probes and it's abstract circuit design. And I think it's anyway something quite relevant, because the more you want to claim things in lower level security models, the more you need to specify what you want, right? In the end, if you want noisy leakage security, that's what Vincent said, you need to say what is the platform, what is the noise that you have, and so on. I think that the threshold, like TIs in general, like first order TIs and all the generalizations, they have properties that are going to be good in general for most hardware implementations. So I think it's how to say, I would even say it's a necessary condition to have these type of things. So I would say at the moment, because we don't see how to directly deal with noisy leakage, the most obvious approach is try to solve whatever you can in the probing model, including non-completeness, glitches, and so on, maybe transitions, and then to use the reductions that we have to more concrete models.
Okay.
So I don't think it will. I don't see right now an obvious case where some relevant gadgets that you make threshold secure is going to degrade security in the end.
Okay, great. So what I'm taking from your answer in your presentation is that typically a threshold approach will improve security, but what we need to be careful about is that we need to look at various models to understand that the positive effects of a threshold approach can be different depending on the model, but typically they will be positive.
Yeah, I think so. Now, if you can, in hardware, right? Software can be different, because threshold approach is really to prevent these physical security order reductions. I think in hardware and also transitions in software, you need to deal with that. Now, if you take like the extreme is this Cortex M0 thing, there's no noise, right? The MI per share is close to 1. So you can do whatever threshold things you want. The main problem is there's no noise, so there's nothing to amplify. And you can put 20 shares or 40 shares if you want, there will be no security there.
Right.
So, but there will be, like if you take the right cases for threshold implementations, I think they cannot degrade, and it's a very good starting point.
Okay. Thank you for the answer.
Thank you. Any more questions? If not immediately, then I propose we have a short break until 4 before we move on to the industry view. We have 2 more talks for today, and then at the end, depending on how much time we have left, we can have a discussion on everything we have heard today. So grab a coffee, have a short break, and at 4 we'll be back again.
hear me?
Yes, but not the presentation view.
Now?
Now it's good. Now it's good.
Okay, so yeah, I'm working at NXP, although what I'll present is my personal opinion, which may differ from a company point of view. So the goal of this is to give you an industry a perspective for specialty implementations against physical attacks. And I'll mainly focus on side channel resistance schemes, although I'll briefly touch the topic for fault attacks, resistance, and combined countermeasures. And then I'll finish with a number of observations and recommendations. Okay, so it's important to distinguish what we as a programmer or a designer have a possibility to control the leakage source. And as already has been pointed out, it differs whether you want to provide countermeasure for software, for FPGA, or for ASIC. In software, since the hardware is built in certain way, you may not have knowledge or ways to influence it, and therefore you are quite limited of a way to prevent certain leakages. For FPGA, you have much more ways to control the leakages, although there are certain things like wiring, which you cannot avoid, and it may cause crosstalk leakage, for example. In ASIC, you have complete or nearly complete control as a designer how you build your circuit. And of course, this allows you to provide better protection. There is another angle also that from software point of view, implementations or operations are inherently processed in sequential manner. And this kind of easily translates to algorithmic description of implementation. While in hardware, you have a lot of freedom in terms of parallelization, order of operations, and so on, which are not always directly translated to easy mathematical algorithmic description of implementation. So in this talk, I'll focus mainly on the hardware ASIC point of view, and also from designer of countermeasures, not as an attacker. So I'll touch upon to several points from theory and practical point of view. And although most of the time I'll be kind of critical to the existing state of the art from theory, I would like to point from the beginning that it's not because I'm not happy to be part of this development for the theory, just because I see still quite a number of rooms for improvement, which are still possible before all this become really mature and well deployed in practice. Models for leakages. It has been already pointed out by FX, for example, that you have several models like noise leakage model, D-wire probing model, bounded leakage model. And the problem is that we have really the deep wire probing model, the kind of the strongest one, which implies security also for the others. But the order of leakages or the reduction depends from constants, which are kind of not always clear what the magnitude of this constant is. Also, it depends on the noise, and sometimes it's required that the noise behaves kind of, let's say, linearly towards the masking order and so on. And all this reduction is not one-to-one relation of the models, which implies that we lose some information there and lose efficiency in that sense. Of course, it's understandable that we have to use this kind of probing model, since this is allowed us, as we have seen the last 18 years, for example, to progress a lot of understanding how to protect the circuits. In practice, one actually is interested how much efforts an attacker needs to put in order to break a system. The efforts usually are measured as a number of traces required to take and then to use in order to mount an attack. Certification labs in the past has been using method to kind of estimate the best attack efforts in order to certify products. Nowadays, we have been gradually moving to leakage detection tests. So not exactly attack scenario, but just a detection. And we know that there's a certain relation between the number of probes in the probing model and moments order. However, there is still not clear relation between moments order and the number of traces required in order theoretically to break a system. And here theoretically means to detect a leakage eventually and not a real attack scenario. So in theory, we still have a room to provide methods to be able to estimate how, on a designer point of view, should design his system, which order or probing order he needs to choose in order to achieve a certain level of security, and this will be guiding him in the design process. So our next point is that ideally we describe circuits as acyclic graphs, which has combination gates and wires, and only few gates are allowed, and this abstraction works. Then we consider probing model, which in general does not take into account timing, and so I'll give a short and quite practical counter example that this has to be taken into account in the modeling. If you consider serial TI implementation, where each component function is processed via a single and unified circuit, and we know this can be done for ciphers like present or also IS, then an attacker who has a single physical probe on the wire and collects this information over multiple cycles, not over single cycle, in fact, is able to collect sufficient information which combined provides or reveals the secret. And this, in fact, shows the difference between side channel and a real probing attack scenario. Another example I want to provide here is comparing the univariate versus multivariate attacks. So, as I mentioned already, we, from practical point of view, look on the minimum number of traces one needs to collect in order to break a system. If we consider the graphs presented here, which are from a recent publication, on the left side, you have the third order, the fourth order attack, univariate attack. On the right side is the third order multivariate attack. You'll see that the three schemes compared here are breakable with a fourth order univariate attack by far faster than by multivariate third order attack. Of course, from theoretical point of view, these schemes are broken because they claim security on third order attacks, which they cannot deliver. In fact, as we see, there's a leakage, but this is by far not practical from point of view of univariate is high order is more stronger leaking. And maybe two more points on this is that the computational overhead here is not taken into account. This is just t-test detection for the leakage. And secondly, in order to illustrate this kind of theoretical flawness of the designs, the authors of the papers have to put a Trojan inside, which they call leakage amplifiers, in order to get a leakage visible. Otherwise, for example, for the first scheme, with 500 millions of traces, still there was no visible leakage compared to 15 million traces in second order. So this does not mean that these schemes are secure theoretically. It's just the difference between reality and sometimes a theory. So some lessons can be drawn out from here. For example, a circuit is not in reality a cyclic graph. And most application implementation are in fact not following this paradigm. So the theory should reflect in the proofs or take into account also this situation, as well as that the attacker or the time the probes are taken is important. And for example, instead of simple probing model, maybe continuous probing model is more relevant. We should more take care about univariate attacks because they are stronger in reality. And of course, we need to compare higher order univariate with multivariate, a bit less order attacks. As already stated, no noise means no security, which equivalently can be rephrased like the larger the noise, lesser order of security suffice. So a designer who can artificially increase the security, the noise, can get better security with lesser order. However, usually the designer has limited influence on the noise itself. And the most maybe important question for designer point of view is how to predict the order of security required in order to achieve a security. Then I come to the physical defaults, which I didn't mention so far. So the glitches, as already mentioned, are one of the most important hardware characteristics. And they led to the fact that ESW scheme became broken. We know that registers are used for stopping the propagation of registers, and they are must in the TI implementations. However, there are quite a number of publications which use dedicated libraries and low-level tricks to prevent glitch propagation. So I think from standard point of view, it should be clear how to deal with such kind of techniques, since at least I'm not aware of a probable way that they can be shown to provide such claims. Other hardware-related leakages are register leakages. However, these are kind of more easy to tackle with, especially for hardware designer. And for coupling, I believe they're irrelevant as leakage on to be taken on algorithmic level, since in most cases on algorithmic level, you cannot do too much instead of increasing your protection order, while on hardware level, low level, you can easily solve these problems. So coming to provable security, as I already said, the ESW scheme has been broken because it was not obeying the TI non-completeness property for hardware. And this property has been introduced in 2006. Only quite recently, it has been shown that non-completeness is necessary condition for secure composition. And even the last year, it has been proven that composition of such circuits which obey the D-order non-completeness and uniformity are secure against univariate adversary. So this is already a good result, as I mentioned, that univariate attacks are really important attacks first to tackle. Okay, still there's a problem. We want to compose gadgets and protect them against multivariate attacks. And a number of schemes which are descended from TI has appeared since 2006. And 2016, a lot of notions has been introduced, NI notions, to tackle the composability, secure composability and formal provability for gadgets. Okay, so what is important to maybe to remember is that all these NI notions provide sufficient but not necessary conditions for secure composition, and they are one way to prove composability and security of overall cipher. So here I'll focus to few detail maybe items which has still to be well defined before some of the theory become explainable for people which are not so deep in it. For example, if we consider gadgets, it's not well defined whether gadget starts and ends with a register or not. Sometimes, or most of the time in fact, in some of the proofs for NI, it's assumed that register inputs are stable, which should imply that we are in register, but this is never stated. As well as the glitch probing for NI, sometimes consider that while you have internal probe, you can get also all inputs for the gadget, which may not be the case since it depends how many registers you have in between the inputs and the internal probe you're posing. A bit to illustrate this evolution of knowledge we have, and also how gradually we get to the state where we are to know well how to protect a circuit. Let's illustrate this with DOM, which is a scheme introduced in 2016, and ESW, which was introduced in 2003, but we modified here with pipeline registers. So they have been proven to be glitch NI, but not glitch SNI. And only in 2018-19, it was discovered or proved that if registers are put at the end of the gadget, then this is a glitch SNI. Then we come to the question of independent inputs. In order to tackle this problem, there are several solutions. Some are not so secure as initially claimed, others are too costly. And only this year we have a proof for something which was long used already, refreshing with sharing of 0. And now it's we have a proof that it is provable secure composition. So this illustrates that the initial scheme of ESW, for example, if we put proper registers for input, output, and pipeline, it become a probable secure gadget, which in other words implies that the TI non-completeness, once it is well understood, meaning proper registers are put in hardware, then the composability become a matter of refreshing and proper refreshing. When I say proper, it does not mean easy. It's a long way we come to here to understand what this means. And even if you look at the publications in the last year or last years, you can see some of them which cut some registers in order to get efficiency, and then the designs become flawed, and by far more had a wrong way to refreshing, and then the designs again become broken. So coming back to the assumptions, TI assumes uniform inputs and guarantees uniform outputs. And while NI does not assume or explicitly assume this for the inputs, and then it leads to easier mathematical proof per gadget. However, this comes with overhead unnecessary sometimes for the gadgets and the composition as a total, because it relies on the trivially composable gadgets kind of strategy. While more efficient circuits could be obtained if we know or take care for the inputs and combine the gadgets accordingly to what the need is. Of course, this comes with higher verification cost. So it seems that I'm running out of time. For side channel and fault and combined attacks, I just want to say that so far our theory and modeling is still not yet to the level for side channel resistance. We have recent progress on the subjects for building this, and it will require a bit more time to get to the same level of maturity, to get to the level we have for the side channel. And the issue also there is that it's harder to test in practice the resistance of schemes. Then I will also skip the explanation for the RSA signature schemes. Maybe you are familiar with them. There's 3 signature schemes which has been standardized and used for quite a number of years. And some of them has been replacing the other standards because they was the only provable at that moment. However, nowadays we all know that they are equivalently secure. It took time to be able to prove that they are as secure as others. The point is that if we don't have a direct attack and the scheme is broken, we still have to consider these schemes because the evolution of our knowledge will maybe lead to the fact that we are able to prove them secure as well. And especially for physical security, we need to remember that our proofs are as strong as the models are, reflecting the reality. And because the models are an approximation of reality, one has to regularly check and validate them. Okay, so my last few slides. For physical security, we need to consider several levels because there are different requirements for different industries, and we need to be able to adapt the algorithms and their implementations to the concrete needs. And it's important also to pay attention for the cost factors. And cost factor is not only silicon, power, energy, and so on, but it's also efficiency. Efficiency in the term of time needed for the designer to design the countermeasure, to engineer, to implement it, for somebody to verify it, and to somebody to certify it, such that we have a product on the market. And products has various requirements, both for cost and both for security. And maybe what is also important to be noted is that some certification bodies, even nowadays, still consider as drawback somebody of using public or known solution or countermeasure, because this gives an advantage for the attacker, so that you are kind of punished because you are using a known scheme for protection. A summary is that we as industry need flexible tools which is able to achieve different security levels and still be cost efficient. This translates to the need to have a variety of techniques and gadgets for the solution. I personally think that we need to focus on order of security which resonate in practice, for example, up to 4th order, although, of course, we can extend this to, let's say, 8th order of security. The number of traces and how this reflects to the order, it's unclear. Vincent already proposed the splitting of 110 to 100 millions, and this is seems quite reasonable. One also should consider whether necessary and sufficient conditions or both has to be standardized in which way. So we need to consider different security level, I already stated. And necessary conditions are must, since they provide already a good level for distinction for what the current state of the art in industry and the certification is. And they guarantee a level of security already higher than the existing one. So if we tackle or focus on different security levels, the higher security levels still may require further leakage detection tests in order to be past the certification. while the lower security levels, the manufacturer can choose which order of certification path of certification he wants to go via formal verification or detection tests. My point or last point is that side channel attack theory is still evolving, and it will become more efficient probably soon. And at that moment, formal verification approach will be further extended to cover even higher probably order of security. And of course, the standard should follow this evolution process. At the same approach should be applied for fault and combined attacks countermeasures, in fact. But mostly at the moment, I think I focus on side channel attack resistance. And that's all. And yeah, sorry, I was too late, too long.
Okay, so thank you, NC. I propose for all the questions, maybe I will pick some of these topics back again for the panel discussion tomorrow. So now I suggest that we move to the second presentation in this session, which is going to be given by Simon Herder from Rambus. So Simon, if you don't mind, please present your slides and maybe give one or two words, just a short introduction about yourself. Simon, can you hear us?
So hello, I hope you can see my slides.
Yes, yes.
Excellent. So I'm Simon Herder. I've been working on certification and security requirements for products with physical security requirements at Rambus and previously inside Secure. I've been in the engineering team. So essentially all my work is slapped with at least one NDA, and you won't find a lot of publications from me. But I hope that I can provide some useful feedback. And it's this presentation is not the opinion of Rambus, and it does not contain information about Rambus products. So what I want to do is I want to convince you that you have to place this effort into a wider context of FIPS 140-X, and that X is on purpose. We noticed that you dropped the DPA requirements from 140-3, and I hope that is because you read the excellent paper from Caroline Wittnall and Elizabeth Oswald on ISO 17825. But so for this presentation, for this talk, there's 5 fundamental questions that I want to raise and that need to be raised at a cryptographic module level when we talk about DPA countermeasures. And just as a small aside, when I say threshold scheme, I use that in a very generic secret sharing sense and not a particular TI sense. So the first thing is the protection order. What protection order do we need to achieve? And if you have a fairly generic purpose device where you get an unlimited number of Oracle queries or traces, then it's very difficult to rule out higher order attacks. Also, you have template attacks and machine learning attacks, which can ignore the protection order because they're doing this combination of shares. They're multivariate by nature. So even if the mass inside, even if it is just looking for an average, it combines multiple samples into one, and there you get that can happen that you get around the countermeasure. And unfortunately, template attacks are very well established in practice and machine learning attacks. They've got some excellent open source libraries they can reuse. There's a lot of people who get trained on reusing those open source libraries, so you can't ignore them when you set up a serification scheme. You have to take that into account. One of the major differences really is that you need this additional learning or training phase, and that's, for example, one use case we're looking at a white box is really nice, because for a white box you simply don't get that learning phase, so you can pretty much rule template attacks and machine learning attacks out. Otherwise, we all know how secure white boxes are. But that's the one nice thing there. So any attack that's not prevented by the device security model that must be included in a certification scheme, or must be considered in a certification scheme. And very much related to this is the number of traces. And there's two really nice examples where you can limit the number of traces, and that gives you a very strong DPA protection. So the first one is chip and pin, at least in the European version. I'm not quite sure how the American system works. I know it changed recently, but if your European chip and pin card has 3 wrong pin entries, then it enters end of life. And that's essentially how much a adversary gets from your real life credit card, unless you cooperate with the adversary to defraud yourself. So that is a very powerful, very simple countermeasure. On the other hand, unfortunately, moving a device into end of life is not always feasible. With a pacemaker, you don't want to move that pacemaker into end of life mode. That would be very unfortunate. Also, you need to have some kind of usage counter or fault counter in non-volatile memory on the same chip, so it's not possible in all technologies. And that already means that whatever security model you're choosing, it has to consider the use case of your device. What kind of device are you building? Key loading is another very interesting topic. DPA attacks on key loading are well known. So you have to store the key in some form, masked form. And of course, that is where, if the certification scheme doesn't check for that, that's where the bad vendors are going to start cheating. And you really want to avoid having something like the European certification for diesel cars, where they just go onto the test stand, and if the test stand detects, if the car detects that it is being driven through a test program, it can turn on all the fancy exhaust cleaning, and if it's not on the test stand, it turns off all the fancy exhaust cleaning. You really don't want to have that in a certification program. So you have to make sure that you choose a correct, good certification program, and that you include this little nasty aspect of key loading. Another thing is talking about side channel protections in AES is all nice and good, but unfortunately, if side channel attacks are in the attack model, so are fault injection attacks, and there are very few devices that can protect a key if the wrong firmware is running on a device. And unfortunately, bypassing the firmware authentication during boot process is usually fairly easy on an unprotected device. So unless you have full protections for the control flow, the adversary will just bypass your secure boot process, load firmware, load their own firmware onto the device, and then read out the use that firmware to read out the key or key shares unless you've hardwired the key loading mechanism, which very few devices do. So again, you have to make sure that you try and cover all the attack paths, and that the certification model also checks for these kind of things. And it may be quite obvious, but again, the use case matters a lot. You have attacks that are very easily scalable, very easily doable, like network vulnerabilities and firmware vulnerabilities, and your threshold scheme in AES, in the AES circuit, it's not going to help you at all if that runs in a machine where the browser has a couple of open CVEs, and you just need to look at a malicious website, and suddenly all your RAM contents, all your keys, all your AES shares get uploaded to the internet. So you really have to be careful where you draw the security boundary for your device, and that is essentially a FIPS 140-140 task, drawing security boundaries. Keep the device simple, have a simple trust anchor in your device, have a clear security boundary, and make sure that this ties in with how you standardize these threshold schemes. So best of the standards cross-reference each other in some way, so that it becomes clear where you put the countermeasure, where you need the countermeasures, and where you don't need them. So where do I think that there is interesting use cases for NIST to become active? Safety critical IoT, that is a very interesting area, because you've got the medical device manufacturers, you've got the car manufacturers, the traffic infrastructure people, the aerospace industry, and they're all creating their own schemes and all asking similar questions about DPA security. And if NIST were to create protection profiles, device profiles, where the crypto part is essentially the same for a small device in safety critical IoT, a big device in safety critical IoT, a device that needs to continue operating even under attack, and so on. And then they could use those device models, those protection profiles, and build their use case specific scenarios around them. And that would make life a lot easier. Another great use case is government uses. So governments are big spenders, and if you know that for a certain government use case I need these requirements, that really helps to define a product, to define where the security boundaries is, to define how many traces do I need to protect against. Can I move a device into end of life or not? Am I going to have a usage counter in non-volatile memory that I can rely on or not? There, NIST can really get really make a great contributions. If you look at payments, for example, it's a different thing. What happened is, if you move the liability to a bank, the bank or the payment processor will ensure that secure chip and PIN cards are being used. And I'm very confident in saying that a European chip and PIN card is currently the most secure, safest thing in European banking. It's much easier to just hold a knife against someone's throat than trying to hack a European chip and PIN card, or to blow up a ATM is much easier than hacking into a chip and PIN card. on the other hand, if you're putting the liability on the end user doesn't choose their chip and PIN code. They get whatever the bank gives them. They're not going to have a chance. So payments I really would tackle via liability and not via some kind of standard. Same in content protection. The content providers, they know the problem, they know what they need, they know what they're doing. Or why change anything in that model if the content providers are happy with existing solutions? So the key to wrap up, my key point really is you need to understand your use case first. That has to come first, and NIST can help with their recommendation and requirements documents and make a really great contribution in those areas. Then you can specify a security model, and that is usually happening within FIPS 140-X and FIPS 140, and how to draw the security boundaries, and then you add details on the certification scheme in an SP 800 or some, maybe even FIPS 140. The approach that was chosen for 140-3 based on ISO 17825, it's not entirely bad, except ISO apparently doesn't know math or doesn't know statistics. So that approach is very feasible, very good. That's how you have to start, and only then you should actually look at particular countermeasures. And on that last point, I would say there are a lot of vendors out there who already have DPA countermeasures in place where it's required. And with required, I mean where customers require DPA countermeasures. So maybe you don't need to do anything. Maybe you need to move forward with NIST IR 8214A, but unless you have specified the use cases where it's going to end up, I don't think you can actually make a specification within NIST IR 8214A that is going to be used anywhere, because it will be very specific. It will be too insulated from the use case to make much of an impact. So that was my presentation, and I'm here if you have any questions.
Thanks a lot, Simon. A really interesting presentation. So I would say maybe just in the view of time, we can probably take 1 or 2 questions to Simon or Venci. And then for more discussion, we can also pick some of these topics tomorrow during the panel in the afternoon. So if you have 1 or 2 questions, please go ahead.
May I ask a question?
Sure.
Thank you, Simon, for the presentation. You mentioned that one slide that if the device security model doesn't prevent an attack, then it must be included. I believe you meant that the attack needs to be included in the model. Would you say that this means that would you intend to imply that then we should have various security profiles where each security profile includes different kinds of attacks? And if yes, would you imagine this as a kind of a hierarchical sequence of profiles, or more a kind of a list of possible attacks, and then we kind of have a checklist where we say, okay, we can handle maybe 3 or 4 of these attacks, but not the others?
So first thing is, if the security model if the device security model says there is no learning phase possible, then of course you can exclude template attacks from your certification scheme, from your device requirements. So in that sense, I'm saying if the attack is not prevented by the security model, then you need to include it in the requirements for the protection profile or for the device. For the device profiles, whether it's hierarchical or not, I assume there will be a cost hierarchy for the device. So obviously a device that has to be secured against 1 billion traces is going to be far more expensive than a device that is secured against 1 million or 100K traces. But from a user perspective, I would more say that the profiles stand next to each other. So in some cases, I can confidently say I've got a usage counter in there that moves the device into end of life mode after 100K traces or 300K traces or whatever you pick. And in that case, I don't need more countermeasures, full stop, because I already have the usage counter. Whereas in other cases, that's just not possible. So I need the big countermeasures. So from that viewpoint, I would say there are equally viable use cases, different but viable use cases.
Thank you.
Any other question?
I guess I could have another question if nobody else has.
I think we can take one more. Please go ahead.
So I think this question can be for both Simon and Venci. So clearly we have this aspect of asking how many traces should we imagine that the attacker can do, and then we can go maybe up to 100 million or even more. And then we have this example that Simon gave where if you put three pins incorrectly, then you're in the end of life, so you don't give more chances for more traces. Do you think that it is conceivable that we can have threshold schemes designed in a way that we can, even if we don't have this end of life setting, like the example of the pacemaker where we can't have an end of life, can we still enforce that a threshold scheme by means of rejuvenating shares and proactive resharing and those kinds of things? In practice, never allow more than a certain number of traces to be measuring the same secret. And so therefore we are in a way limiting the number of traces that are actually feasible to take to a number that would be much lower than 100 million, let's say.
If you have some other way, sorry, go ahead,
No,
Nancy.
go ahead. Sorry, go ahead.
So it's not the lifetime of the shares, it's the lifetime of the key that really matters. And if you have a way to refresh the keys on both ends of a communication, of course, that is an alternative to moving a device into end of life. If you don't have that method, you can still tackle it of attack cost versus asset cost. So an asset that cannot be end of life should not protect something very very expensive, very sensitive.
Maybe I can make just a slightly more specific point. So with respect to the key, let's say that we have a key that for some reason needs to be used for a long time. Can we still, let's say, you gave an example of the key loading aspect. which may be a point of attack, can we consider that just because we actually don't store the key bit by bit, but rather we store the key in a shared way, if we say that after a number of uses, we always create a resharing of the same key, do you think it's possible to assume logically that in practice we don't have the same key, and therefore we don't have the same, and therefore we can limit the number of traces that are attacking each key?
I think, okay, sorry. I think in scenario for side channel attacks, we kind of assume that each execution, so each trace you take for IS execution, you have a different sharing of the key. So the key is plain in the beginning, but then each invocation you provide randomness and get new sharing. And this does not prevent, I mean, it improves protection, but still, let's say 100 millions or 1 million of traces will break the system. So just resharing what I wanted to say of the key may not suffice. It's more about changing the key itself.
Okay.
And to add to that, specifically for the key loading, if you look at secure boot keys, for example, they're usually stored either in OTP or in a puff. And that means you cannot change that aspect of the key. So okay. You maybe if you have an additional part that is stored in off-chip, then maybe, but that's going to cause another host of problems, because off-chip storage is not always accessible during boot time. And if you make that accessible during boot time, then you can run into other security issues within your module that are not related to AES. So that's a very difficult, it may be a viable path, but it's certainly not going to be an easy path that every chip can do.
Okay, thank you for the answers.
All right, so Simon, Venci, thanks a lot. So Svetla, now just looking back to you, do you want to give any last words for the tomorrow agenda? And
yes, so tomorrow we have 2 more presentations in the first part, and then we plan to have a panel discussion at the second part of the day. So probably we'll ask people from who presented already today to be included in the panel. We'll still have to discuss who will be exactly in the panel. But yeah, if you have already any thoughts or anything that you want to hear specifically, if you have any specific questions to people that presented already or who are included in the list, you can say now or send email to me before tomorrow afternoon, so we can take this into account. Otherwise, if no more questions for today, I would close the day. And
Svetla?
Yes.
I think somebody just asked in the chat if we could get the slides. Will you be making available all the slides?
Yes,
on the
yes. The slides,
today?
actually, most of them are already online on the website. I hope everyone knows the website, but I'll put also the link in the chat. And now I'll add the rest later today when we finish the meeting.
Okay, thank you.
Any other comments, remarks?
yeah, maybe just to add what Svetla says, basically the one idea is to have tomorrow's panel a little more industry oriented. So if anyone here has questions regarding the talks from Simon Venci today, please email this to us today so we can discuss it in the panel more broadly tomorrow. But again, not only industry, we will also address the academia points.
Yes. So if no more questions, I would like to thank all the speakers today and all the participants. I hope you enjoyed the presentations and you gathered useful information. And hope to see you tomorrow at the same time, and use the link that I have sent. Links for every day separate, so there are separate Zoom meetings. Please use the link for the second day tomorrow at the same time.
Thank you.
Thank you.
Thank
Bye-bye.
you. Thank you. Bye.